webinar now. So again, thank you everyone for participating in this webinar, and we will begin our discussion on NAVAIDS now. Again, if you have any questions at any point, just enter your questions in the question field below. So today, our focus is going to be discussing navigational aids, also known as NAVAIDS. We're going to go over specifically ground-based aviation NAVAIDS. We'll discuss a little bit frequency allocations for NAVAIDS, and then we're going to get into more how approach is supported by various NAVAIDS, in particular Localizer and glide slope, which are part of instrument landing systems. We'll talk about the frequency pairing, calculating threshold crossing heights, determining gradient slope, and intercepting the gradients, the glide slope. We will have a demonstration on spectrometry in the middle of this part of the presentation, and then we'll get to another part of the presentation where we'll talk about propagation, interference, frequency coordination, and we'll do more demonstrations at that stage. So understanding NAVAIDS. Any sort of device or what is a navigational aid? It's any sort of device or marker external to the traveler that assists a traveler in navigation. So this can be, these are usually related to aircraft or ship-based navigations, and this can include, but not limited to, lighthouses, buoys, fog signals, beacons, ground-based radio stations, satellite, etc. However, this demonstration will focus on modeling the following RF aspects, radio frequency aspects of ground-based aviation NAVAIDS with the spectrometry technical analysis module. So we're primarily going to focus on radio frequency propagation, interference, and frequency assignment a little bit. But we'll probably discuss frequency assignment, how that works, but the primary demonstrations will be propagation, interference, and some of the items I mentioned earlier about approach, calculating approach. So ground-based aviation NAVAIDS, we're going to briefly illustrate a number of them here. These include, but are not necessarily limited to the following: Vhf omnidirectional range. There's a screenshot at the left of what's known as a VOR NAVAID. And a VOR NAVAID is a VHF broadcast radio tower that broadcasts NAVAID signals that spin so that an aircraft can track a specific radio and navigate using the radio course. This allows the pilot to be sure they are navigating the proper course despite wind and magnetic errors that may occur when tracking a raw heading, also known as a dead reckoning. Operates in the 108.1 to 117.95 MHz frequency band, may be located either on or off airport facilities. You have the distance measuring equipment, also known as the DME, that communicates a number of miles the aircraft is from the VOR. VORs are usually paired with a DME station, known as a VOR DME, and that is used to provide bearing and range information to an aircraft. You also have what is known as a Tactical Air Navigation System, or a TACAN. This is a more accurate militarized version of the VOR DME systems. A TACAN station may also be paired with a VOR station to form a VOR-TAC station. There's also non-directional beacons. This is an older type of NAVAID, not as popular anymore, but it's an AM broadcast radio tower that does not broadcast a direction or a vector such as a VOR, but general bearings. The bearings are known as QDM and QDR and communicate the magnetic bearing to and from the NDB station. Subject to atmospheric errors caused by thunderstorms, etc. While it can provide a longer coverage than VORs, it tends to be less accurate. And as mentioned before, it's used less and less, in particular in the US, as it's being replaced by GPS. And GPS is actually starting to replace a lot of these NAVAIDs, but not so much. We'll talk about that in a moment. So we're also going to focus a lot today on the instrument landing system. Its instrument landing system is composed of three principal components. It's multiple components, but the three that we're probably going to focus on some today is the localizer. The localizer is a component of the ILS that provides left to right guidance for the aircraft. So if you can see in the diagram, You have the threshold at towards like the center left part of the diagram. It's black strip on the ground there, and it's got like a blue kind of line kind of extending from it. That's the path of the aircraft as it's trying to descend and approach the runway. And so the localizer helps provide this left-right guidance to make sure that the aircraft isn't too far right or too far left of the runway. You have the glide slope or glide path, and it provides vertical or up and down guidance, and marker beacons that provide distance information to the runway. So you've got outer markers, middle markers, and inner markers. Outer markers usually maybe as much as 7 nautical miles away from the runway. I think the middle markers are around 1 to 3. And then the inner markers are usually within a few hundred feet to 1,000 feet, but inner markers aren't actually used as much anymore, really. You also have something called Gbass, or Ground-Based Augmentation System, which is part of the Global Navigation Satellite System, or GNSS. This system helps provide GPS corrections to an aircraft on approach. This is more next-generation NAVAIDS and will probably eventually replace ILS, as it is more precise and less expensive to install, but that's going forward, and this will be for more modernized airports. So for most jurisdictions, classical ILS, VORs, DMEs will be things to still have to consider in terms of interference and frequency coordination. One thing that should be mentioned is that Gbass does still work in the frequency bands organized for ILS, for the localizer in particular. So from a spectrum point of view, there's some of the principles of mitigating potential interference with the Gbass could still apply, and actually would have to be maybe new methodologies would have to be developed to mitigate the potential interference issues. Now, to give kind of a spectral context to these NAVAIDS, I decided to organize some screenshots from Spectrum's Spectrum Planning module that highlight where the NAVAIDS would fall in the allocation chart. So here I've zoomed into the 0.1 to 1 megahertz frequency band. So this is under 1 megahertz, principally LM, LF, MF, HF bands. So you have here the allocation. You have what we've marked here as navigation type NAVAIDS. These are things such as the NDB or different types of locator beacons operating under 1 megahertz. And if you zoom out a little further, you can go and you extend the range out to 100 megahertz. You can see where other NAVAIDS, which are maybe more air-to-ground communications, operating in HF band, and other types of navigational aids, such as marker beacons, operating about 75 megahertz, would appear. So you can see there's anything that's related to navigation usually is at a lower frequency band because it can offer more range. You'll oftentimes under VHF, MF bands, HF band. Certain ground comms NAVAIDS are also in the HF band for that purpose. So modeling MF and HF propagation is important to properly model the range of various navigation and communication type NAVAIDS. If we zoom out a little more, we go between 100 megahertz and 2 gigahertz or 2000 megahertz. You'll see that there's even more NAVAIDS that start to cover these frequency ranges. I've highlighted a few. You've got some, actually these are maritime NAVAIDS here, EPIRB, ELT, and you've got some satellite comm NAVAIDS. And then you've got the navigation NAVAIDS that we're going to focus on. So you've got the Localizer, VOR, Gbass, glide slope, DME. This is all operating within about 100, 108 to 117 megahertz, a little higher. Glide slope is around 340 some megahertz, and the DMEs are in typically could operate around the 900 megahertz band. But you also see SATCOMs. These can also be used obviously for navigational aids. and they tend to operate in the higher UHF band and they go further into the SHF band. And surveillance NAVAIDS, these are radars such as primary surveillance, secondary surveillance, or monopulse primary surveillance radars. These tend to operate in the higher UHF bands, and we're not going to get to them too much. One of the reasons we're going to focus primarily on navigational aid aircraft, ground-based aircraft navigational aids, and modeling propagation interferences. There's very clear-cut methodologies and recommendations from international organizations on how to model and analyze and mitigate potential interference issues with other terrestrial systems or ground-based systems such as broadcast or mobile transmitters. In the case of radar or satellite, there isn't as much of like references you could look at, such as ITU or ICAO, that are define how to mitigate potential interference with radars or satellite systems. There are regulatory organizations such as the NTIA in the United States, the FAA in the United States, Ofcom in the United Kingdom, that do have some notices that describe some methodologies on how to mitigate potential interference between, let's say, mobile or ground-based communications, RF systems, and radar systems or satellite systems, but they tend to be kind of unique, almost sometimes artisanal approaches, and may not be applicable to other jurisdictions without a lot of kind of re-engineering, for lack of a better phrase. So today, this is going to be our focus, is the ground-based aircraft navigational aids. But I wanted to give a frequency context as to where we're working on. We will go a little bit in the modeling some of the beacons, the marker beacon NAVAIDS, the below 1 megahertz NAVAIDS to show that our system is capable of handling propagation in those bands. And in a separate demonstration, at another time, we'll also discuss how we model satellite systems, propagation and interference with satellite and radar. Like I said, it's a little different, and it requires kind of a different approach to the presentation. Now, as far as channel assignments for ILS, instrument landing systems, there's about 40 pairs of localizer, glide slope, or glide path frequencies. I will use that term interchangeably during this demo because that's how a lot of the documentation is written. So glide slope, glide path mean the same thing. Localizer frequencies are typically in the Vhf band. They're longer distance, and glide slope frequencies are in the Uhf band because they're generally shorter distance communication requirements. So here you have about 108 to 117 for the localizer, and 330.95 to 334.7 for the glide slope. Here's an example of the channel assignments, the pairing. And as you can see, the pairing is orthogonal. So the idea is to avoid having a frequency reassigned for the localizer or the glide slope that is going to be reused in the same pairing. So the navigation receivers are typically or automatically tuned to the glide slope when the localizer is tuned due to this pairing. So this is kind of programmed into the equipment. And I mentioned before, marker beacons always operate at 75 megahertz. They also make up part of the ILS. Here we'll talk a little bit about threshold crossing heights. So here we have a diagram or a snapshot on the left of an aerial photo that shows a glide slope antenna next to a runway. And so you have here the antenna on the left and then a line connecting, kind of pointing to where the antenna would run perpendicular to the runway. And see it's about 90-degree angle and 173 meters from the runway. So this is the position where the glide slope antenna would be facing the runway is known as the glide slope point of intercept. And that's exactly what I've written here. It's a spot on the runway that is perpendicular to glide slope antenna. Spectrum includes a calculator that, taking into account information about the angle of a descent from the plane, the position of the glide slope antenna, and the information about glide slope gradient, can calculate what is known as the threshold crossing height. So the threshold crossing height is the height required for the plane to be at in order to safely approach and land on the runway. So in the diagram here to the right, you have an extract from FAA Order 8260.3, and this provides a formula for calculating the threshold crossing height, or the TCH. This is on ideal terrain, which is flat. So you have here angle of descent specified by the theta symbol, and you have the plane's glide slope, and you have the glide slope antenna marked here, and the glide slope point of intercept, or the GPI, at about the same point as the runway point of intercept, and the distance between the threshold crossing height and the glide slope point of intercept is marked as D here. So this is where the GPI is at the same distance in the profile as the glide slope antenna. There are considerations to be made if the terrain is sloped. So this is not common, because you typically want to have an airport on the flat terrain. So that's why airports are usually, flat environments near the coast. It's very common, but sometimes you have no choice. So the airport may be a little bit of a sloped terrain. So in the case of sloped terrains, the formula changes a little bit. So the figures above serve as examples where the terrain slopes down and up from the glide slope to the runway threshold. The figure on the left demonstrates a case where the terrain slopes up. So you can see the plane coming down here from right to left along this glide slope line, and the terrain is this thick black line, and it's kind of sloping up. So in that scenario, you would have the glide point of intercept, glide slope point of intercept, potentially behind the position of the glide slope antenna. And you have the inverse effect if the terrain is sloping down. So here you have the glide slope, or the glide path of the aircraft, and here's the runway, and you can see the terrain's kind of sloping down. In this case, the glide slope point of intercept would be much earlier, before the glide slope antenna. So what that affects in terms of the threshold crossing height is that the height, the TCH, changes. It is larger when the terrain slopes up and smaller when the terrain slopes down. That's important information when being able to consider when calculating the TCH. So the software Spectrum allows you to determine the terrain gradient slope. So some airports will publish the longitudinal terrain slope in terms of percentage. Given this information, the user can input it into the TCH calculator included in Spectrum E. The percent value is input in the user gradient slope by pressing No in the Calculate Gradient Slope from Terrain option. You press No here, this option becomes activated, and you can enter in your custom gradient slope. And that would typically be provided in an aeronautical chart. So you have here an example of how that is calculated, and that again is taken from an FAA directive. Alternatively, if the user wishes to see the terrain crossing height with Spectrum E's calculated longitudinal terrain slope percentage, and this can be determined if you have access to high resolution digital surface model data, or DSM data, such as 1 to 5 meter resolution, then you would be able to calculate yes, and in the calculate gradient slope from terrain. And then in that case, the software will take the terrain data from the software, and we'll be able to calculate the slope accordingly. So you wouldn't have to enter in a slope manually. But again, that's really only recommended if you have 1 to 5 meter resolution data accessible to you. We do cover in Spectrum E many airports in the US, about in close to 50 airports in the U.S. at 1 meter from LiDAR sources, and a number of additional airports around the world, including in Europe. So intercepting the glide slope. So here we have a screenshot of an aeronautical chart that describes how the glide slope intercept is to be performed. So you have here the glide slope in this thick black line, and you have different type of markers of distance, and I believe these are feet. And well, actually, down here this is nautical miles in distance from the runway, and then these other markers here, they're measuring feet in the air, so 1,500 feet, 2,700 feet, 3,700 feet above the terrain. So you have here this kind of a gray feather, which helps describe the angle of approach to the runway. The runway is this dark black line to the right here. So you have a middle marker located usually about 1 nautical mile or so, is typically the point of no return from where the pilot must decide if they'll attempt a safe landing or if they'll execute a missed approach and turn back and try again. And so this is the middle marker here, and this is, you can see in the diagram, is where the pilot will make a decision at that point if they're going to actually try to land or not. And here you have a little diagram that shows this, they may decide to execute a missed approach and try a landing again. So that is the middle marker there. And then you have at the outer marker about 3.7 nautical miles. That's like the first marker that the pilot would receive a notification that they're approaching the runway. The right side of the chart here, it describes the distance from the TCH to the glide slope point of intercept to be about 1,030 feet. So taking that information into account, it determines that the TCH, or the threshold crossing height, to be about 54 feet at a 3-degree glide slope. So it tells you what the glide slope angle is here, the theta angle in the formulas. And so this is also something that is determined by our software. As you can see, we did the same calculation for this example in our software. And so you can kind of just confirm that, or if you don't have access to an aeronautical chart, you can ask the tool to tell you this information. So we'll begin the first demonstration today. I will go ahead and switch over to Joel, who will take over. So let me go ahead and switch to Joel as the presenter. Presenter. All right. So Joel, whenever you're ready.
All right. All right. And can you confirm if you can see my screen?
Yep, I can see it.
And do you see the browser yet, or?
Yeah, I can see the browser. Hands up if, let's do a hands up if everyone can see Joel's screen.
All right.
Okay. Let's see, let's just try to confirm if people, yeah, I see hands up. Okay, great. Thank you, Robert. Thank you, Barbara. Okay, so you can go ahead and begin, Joel.
All right. So as you guys can see in the network page, I have set up a few items, mainly the TCH and the GPI points along 2 runways. And that is for the Dallas airport here in Virginia. And as you can see, I'm gonna highlight these 2, and I'll be working with those. Right now on the info field, this is blank, so I don't have that information for the TCH that you would typically find on those charts that Daniel was showing you. And I'll show you a layout on the map of how it looks like. So here's runway 19R, here's runway 19C, and just as a helper, I added the ILS where it's located here. But for this purpose, we just need these two items. So for calculating the TCH height based on the angle, the vertical angle of descent, you basically interact with the map. You zoom into the area of interest and you put in the threshold crossing height point over here. As you can see with the high-res imagery, you can zoom in very close on the map and you can put it in at the beginning of the runway.
Joel, I think you're using a dual screen. We can't see
Oh,
the screen.
sorry.
Sorry, you can restart. That should have notified you.
Yes, I'll go ahead and show again my screen here.
Can you kind of turn off the dual screen just in case, because it will maybe mess with the resolution on the recording.
All right, it's off.
Okay.
And as you can see here, I have the items that I was just describing. I have the TCH and the GPI points. And those are the ones that I'm describing here on the map. Here's the TCH1 on the runway 19C. You can see the name here on the actual road or runway. And as I zoom out, you will be able to see the GPI point, and you can actually even see the GPI, the glide slope antenna here. And zooming in, you can even see where it's actually located. We have different tools on the Spectrum E that allow you to intersect on the runway where this point should be located. So in this case, it's perpendicular to the runway, as I just did right now. And here's a picture that shows both runways next to each other. And I'm gonna be using 19C as an example. And as you can see, it has blank information right now. But once I select both of them, both of those items, and I go to the update TCH calculator, then as Daniel was describing, we can change our vertical descent angle as we like. But in this case, I'm gonna leave it as the default, which is actually what is in the published charts. So just as an example, this is an online resource that gives you different access to different charts. And this information is gonna change depending on the type of airport that you have. So as you can see here, I'm gonna have the 19C runway for category 2 to 3. So once I select that, I would actually end up in this chart. And that's the chart that Daniel was showing you. And if I zoom in so you can see better, you will see the distance that I'm expecting to calculate for the runway for those 2 points, which is 1,030 feet. And based on that, with a vertical descent angle of 3 degrees, I should be able to calculate a threshold crossing height of 54 feet. And once I execute this, that information should be validated in tool. So if I go over to the right side, you'll notice that I do get those same the same information for these 2 points. And of course, the distance is being measured from the resolution of the terrain that we have in Spectrum E. So you do actually get that. And as Daniel mentioned, the higher the resolution of the terrain, the more detailed and accurate your measurements will be. So that's essentially how you calculate the TCH in the case that you can't find the charts and you would like to know what those values are. A reason why that might be important is because, as Daniel mentioned, you have a certain angle of descent, but let's say you have a different angle that you're arriving at that threshold crossing point, and you wish to know what should be the height that would be safe for you to land the airplane if that angle is different. So we do have some users that use the software that do change this vertical descent angle to something else. So for example, let's just say I'll change the angle by 1 degree. So it's 4. And I hit execute or OK on this one. Then I can come in and I will notice that it says that if I come in with a vertical descent angle of 4 degrees, then my threshold crossing height for my airplane to land safely should be at 72 feet instead of the 54 that was there previously. So we have ability to be able to take in consideration the high resolution terrain that you have on the map to perform these calculations, and play around changing the different vertical descent angles to determine the safe TCH height that your airplane should be at when it arrives at the threshold crossing height. And that closes this part for the TCH demonstration.
Okay, thank you, Joel. So I will switch back to my screen. And can everyone confirm if they can see my screen? Okay, great. Thank you. Thank you, Barbara. Thank you, Roxana. Thank you, Ian. All right, so here I have an example of a high resolution data set in Spectrum-E. And one nice convenient aspect of Spectrum-E is you don't have to load these data sets. You just log into the system, the Spectrum.Center portal here. And if you have appropriate login information, you should, and the appropriate subscription level, this is accessible to unlimited subscribers, you should be able to access this information. So here you see I'm zooming in here to the airport, and there's a little 3D button that I can click on that will render the information in 3D within the browser. So here we go. Now I can see that I do have this airport in 3D. You have the runway, you have the airport here. This is, I think, Reagan National. And you even have, this is LiDAR information, so you have the trees and heights information. You have the different towers, etc., that appear there. So this is the kind of level of detail you would need to properly get a good calculation of the TCH. If you were to use the terrain data included in the Spectrum to help calculate the slope of the terrain. So I think most U.S. airports are pretty flat, so this would probably be more useful in other airports in other parts of the world. But I don't know. I'm not an expert on all the airports in the U.S., but for sure Reagan is pretty flat. So you could probably just work with the input of 0 or whatever is recommended in the aeronautical pilot chart for the slope of the terrain. So we'll go back to the PowerPoint for the moment and go over a little bit more on the presentation that we have here. So we're going to now talk about propagation, and then we're going to get into interference and frequency coordination. So can everyone see the PowerPoint on the screen? Just want to make sure. Okay, thank you, David. Thank you, Ian. Thank you, Alistair. Okay, great. So we're going to first talk a little bit about Mfhf propagation. So this is important for certain types of long-range NAVAIDS, particularly NAVAIDS that are for assisting in guiding an aircraft while it's flying. Not so much necessarily for approach, because once you're in the approach stage, you can rely on VHF or your UHF systems. So as you can see, you have here two models that we recommend. One that models the ground wave phenomenon, one that focuses more on the skywave phenomenon. So in the case of ground wave, the model that we typically recommend, and there's some different models out there that we also include, but the kind of the internationally recognized model is known as the 368 from the ITU. And in terms of the skywave phenomenon, it's the 533 from the ITU. So this would be a good example here of using NDB. There's some examples here I have of NDB stations in Latin America. that are using these. The NDB equipment is used to help guide aircraft as they're flying or en route. You can see the examples of the coverage on the. Joe, can you stay on mute for a second? Thanks. Examples of the coverage of ground wave on the left-hand side. Pretty extensive, going several nautical miles out from the coast. You see several ground wave stations here, NDB markers that cover a good chunk of the southern cone of Latin America. These are Chilean airports. And then you have here some examples of the skywave day-night coverage, where the coverage changes on an hourly basis according to the model and sunspot number index values. So I'm going to highlight that now a little bit in the software. So let's go ahead here. So here's Spectrum E. Anyone that would like to trial Spectrum E, feel free to go to spectrum.center and click the request access button. And then there's a little form that you can fill out. You can specify what modules you want to fill out or any other message you want to send us. And we usually engage with these requests and help provide at least a 1-week trial to any customer that's interested. For most any of the modules. Some of the modules have some dependencies, such as the monitoring module. You would obviously need to be able to communicate with a device. So that for those cases, we may organize a demonstration. Okay, so we'll go ahead and log in. Once you have credentials, you can log into the system. And here we go, I'm inside of Spectrum E. So I'm going to go to the part that has to deal with engineering. So I have here a network that I've already created, and you can see we have several objects here to model. One nice thing about Spectrum is as you click on a different object in the drop-down menu, the relevant functions update, so you're not confused about what functions, what models to use when you're modeling a particular type of object in the system. So you see I have here about 8 HF stations operating in multiple frequency bands. If I click on any one of them, I can see the input parameters, the model number of the antenna. I can pick them from a list of antennas, and I have a whole library of HF antennas, which I can look at here. And the unique thing about HF antennas is that they change per frequency. So as I click on changing the different pilot frequency here, the pattern itself will change. And this is a text file, this H3D file. Can be uploaded as a CSV, so if you want to add additional antennas, you can do that. And so we have some manufacturers and stuff that we work with that help provide this information. And so we have a decent library, but a lot of times there's unique patterns or new patterns that our customers may want to use, so they'll add their own. And those patterns can be stored in our public library or in your own specific directory. So each user has its own account with their access to their own data. So if you have some antenna patterns you don't wish anyone else to use, then it can be stored to just your specific account. So I have here a number of different patterns to assign to each station, and I can run the calculation. Now this calculation will run across the entire planet, 24 hours of the day for, here we've got about 7 frequencies. So that'd be a pretty heavy calculation. I already finished it, so I'm just going to produce the result. So I'm going to click on the composite SNR button. Let me select all. Composite SNR. We'll do downlink. There you go. So here I have a pretty interesting display. I might change my map to make it a different type of background. The nice thing about Spectrum E is you can kind of rotate the map view to any perspective, so you're not stuck in the typical east-west type display, but I can rotate it here. And this is actually fairly useful for Asian Pacific customers, as well as customers like the U.S. Coast Guard or the U.S. Navy that prefer this kind of view of the planet. So as you can see, I have here the coverages from the different stations. You can display their labels. Should probably be a good idea. become a little more obvious where the stations are from. So here we got my San Francisco, Alaska, Honolulu, Guam, and I can cycle through the coverages if I wish by clicking on the Universal Time button, and that will show like a little movie of how the coverage is changing at different hours of the day. It's a very kind of unique capability. Spectrum is one of the only tools I've seen, comprehensive spectrum management tools that have this capability included. And there's a lot more to it that has to go with automatic link establishment and other types of things when it comes to modeling HF type communications. But this is a pretty common type of feature. So you can also do things such as calculate a probability of coverage. So this would be a composite in terms of percentage. So calculating the coverage at every hour of the day, but turning that into one single composite percentage. We'll do like an SN of 5, and we'll be downlink. And so that kind of simplifies the output. Let me go ahead and to just a single output, but as you can see here in terms of probability. So anything that's blue is 88 and up to 99%. So you can see most of the region here is covered, and the Pacific is covered up to 99% with these 4 stations, these HF stations here. And if I move the cursor around on the map, it'll tell me a different reliability here at the bottom. We move down to the greens, it'll say 91.7 down here. We'll move down to the other parts of the coverage, the heat map here, to 95.8. So I can toggle between my predictions if I wish, and go back to my SNR prediction through the predictions menu. And I can output the same type of information here and like cycle through it. Here I have my legend changes, so it's 5 to 50 dB. If I want to change that, I can always adjust it. If I want to raise it, let's say 10 dB SNR, I go to click on the palette button and I can change my threshold there. So the threshold is pretty dynamic. As you can see, it changes based on how I define my palette. So if I wanted to highlight that, we'll go back now to the PowerPoint. So here I'm now just showing the next part of the PowerPoint, which has to do with Vhf and Eurojet propagation, also important for modeling ground-based aircraft or aviation NAVAIDS. So you have basically propagation models for aviation NAVAIDS organized in 2 categories. We call one category below 1 kilometer AMSL, or median, average median sea level. So anything below 1 kilometer AMSL generally would be low-flying aircraft, such as helicopters, drones, or small aircraft. So that has very different considerations to take into effect when it comes to modeling propagation. So the relevant models will be different. The models that have been recommended by the ICAO include the regular terrain model, also known as long rise, the EGLI model, and the IPORP 526. It's a kind of a comprehensive diffraction model. All these are recommended, and they're included in Spectrum E. So you see here some examples of propagation for lower flying aircraft and what the coverage heat map can look like inside of the Spectrum E tool in the VHF range versus the UHF range. One thing you'll notice is the heat map contour, or the extent of the heat map, is much larger in the VHF range than in the UHF. This is the same kind of a map and same stations, but just operating in different frequencies. So as you can see in the VHF range, the signal going out to -115 dBm goes out pretty far, several kilometers beyond the coastline. But in the UHF range, it's a little shorter. It's still pretty far off the coastline in certain angles, but not as far as in the VHF. So you can compare like the difference between ILS, localizer coverage versus flight slope coverage for an example. Then you have coverage above 1 kilometer AMSL. So this would be more for high-flying aircraft, commercial aircraft, communications commercial aircraft, marker beacons, for example, that operate in the VHF band, VOR, DME, NAVAIDS operate in the VHF band, DME goes up into the higher UHF band around 900 some megahertz. So there's a different model recommended for that because of different phenomena that occur when you go at a certain height into the atmosphere. There's a model known as ITR P528, which is the most well-maintained model for ground air communications for high-flying aircraft maintained today. There's some other legacy models known as Johnson Gearhart or IF77, but I think a lot of those considerations have been wrapped up into into the latest revisions of the 528, which also do incorporate 526 diffraction modeling. So that will help create like shadow effects if there's mountain ranges and stuff to take into consideration. So if we look at an example of that model here, you have the configuration box here on the left in spectrum and then an output on the right. You can see that it is considering the terrain. So you do have some shadowing and fragmentation into the mountain ranges on the right here off the coastline. But when there isn't any, you don't have the same type of fragmented effect that you had with the other models. You have more cleaner effect. And this is assuming that the receive point will be way above in the air, to the greater than 1 kilometer, like greater than 10,000 feet. You have different considerations that may be taken into account. There's loading effects. There's different type of atmospheric phenomenon that can impact the coverage and have it extend further than might be expected, or create different types of effects. So that's covered well with the 528. So for Vhf propagation, I will hand over to Joel again, and he will take over from there. So I'm going to go ahead and make Joel the presenter. Turn on your microphone, please.
Right. So you guys, showing my screen now, and I will be showing coverage analysis for the models that Daniel was just speaking about. So as you can see here, I got two objects. I'm going to be using the lower one here labeled as TX to demonstrate a coverage for this object. And I'm going to remove the one that is on the map right now. So I'm going to zoom out so you can see the area of interest. And essentially what I'm going to do here is it's going to be basically a hypothetical coverage to demonstrate how a user can use the tool to do a high altitude flying object versus a low altitude flying object, and what considerations they need to take in order to get a proper coverage display. So this is typical if you're doing for example, military exercises where you don't necessarily have a commercial flight path that is predetermined and you know is clear of obstacles. You go to an area to do a military operation, like for the Air Force or something like that, you want to do some exercise and they might be random, and you want to fly it in an area, and you need to know the area that you can actually fly in and is safe to fly around, and then plan out your flight path accordingly. So the tool can help you do that. So if we select, for example, this transmitter object here, and I run my 528 path loss coverage, so I'm going to be simulating a flight path at this height, and the calculation distance up to 200 kilometers. You can change that as well. As you know, or you may know, some of you may know, that the 528 has a certain time availability in percentage that is used to calculate your coverages. By default is the 50% for planning purposes. But the model itself is built on top of the free space losses, but after 1 kilometer, the power received, it's not purely based on free space. It is based on the measurement curves that were implemented into the 528. If you look it up, you'll see some graphical charts that show you per frequency, per time of availability, and most importantly, on the height of your object, the altitude that is flying at, it changes how the power is received at those altitudes. So given that this model it's founded on this implementation of measurements and curves, there's two ways to run these coverages. One is without a line of sight filter, which is purely using those curves that I just described. And the other one is using the line of sight filter by saying yes. So, and when you say yes, then it incorporates the diffraction model that Daniel was speaking of in the PowerPoint. And that is used more for the low flying objects like helicopters or some drones or anything like that. So I'm gonna show you what it looks like with both type of coverages, using everything the same, and the only thing that I'm gonna change is the line of sight filter. So in this case, I have it as no, which means it's just gonna be a pure 528 coverage analysis. So when I run it, it's gonna execute this coverage. I then select my object, and I'm gonna do a display of this coverage in dBm, and I will leave the name by default and run this. I'll zoom in so you can see it a little better. So in this case, for this exercise, this is the area of interest that I want to do my flight path and training exercises. And if I just do the 528 alone, I will see that given the required threshold, I can fly it all around this path. Now, the reason why I have this RX object here is because I know that this is behind a cliff, and that's why I want to show you guys that since it is behind a cliff, and at this altitude that I said, which is a low altitude, it's below the 1 kilometer, it was 277. I know that I will not be able to fly at that height in this direction. So since my interest is mainly this low flying path for tactical exercises, I'm gonna go now and do the same thing, but take in consideration the line of sight filter. And this time, when I go and redisplay my coverage, I'm gonna overwrite the same one that I had with the same name. You will notice now that it's more accurate. And you can see how it's curving into the terrain there, and it's showing me where I cannot go into and fly in the low path altitudes for the exercises that I want to do, and it does show me the areas that I can. So just to give you a better picture of what is going on, like from a different perspective, I can show you what the terrain profile looks like going to that area. So as you can see, there is this obstacle, big obstacle here in the way, and the altitude of the terrain itself is at 277, which is the flight path for the helicopter or drone or that I wanted, the low flying altitude object that I wanted to simulate. I ran it at 277. So as you can see, the receiver is at 277. So I not only am blocked at the receiver there, but I'm blocked along the path as well. And my TX is actually at a very low altitude. So that's why the area of the flying area after applying the line of sight filter is very short. So as you can see, it would actually be from this area here and going to the right, but not coming into the receiver. So that's exactly what the map was showing. So it's showing that I can only fly up to this zone right here, but not any further at that given receiver height that I input in the model. So those are some of the technical aspects and important considerations to take when you're simulating air to ground or ground to air coverage simulations in the tool. So that concludes this part of the presentation.
Okay. Were you going to show any about the gain calculation?
Oh, I can show that now. I was going to show it at the end, but okay. All right.
Yeah.
We now for the what Daniel was mentioning is the for the ground communications coverages for the ILS objects, for example. So I have another network that I have here to demonstrate that. And in here, I have two ILS objects. They're actually the same. It's the same object, but it's a different. I want to show you two different ways to run these coverages. Now, in this case, you see one has an antenna and one doesn't have an antenna. So if I show you the one without the antenna, it's actually an Omni, and it has the same exact parameters as the one with the antenna. The only difference is the antenna. So you can see here the horizontal and the vertical patterns that I am using. And I'm gonna show you why this is important when you're running coverages for the ground-based objects along or inside an airport area. So I'm gonna start out with the Omni coverage first, and I'm gonna do a ITU 525 line of sight coverage. Now, for this, it depends. What you want to set here is depends on what type of object you have. So if you have an ILS, a VOR, or a Gbass object, that for Gbass, you would look at the ITU 1841. For ILS and VOR, you look at the ITU 1009. It has specifications there as to what the receiver height should be and what the calculation distance should be for your coverage areas, the area of interest that you want your energy to be received along the airport area. So I'm gonna put this in for the ILS from the ITU 1009. I run that, and then I'm gonna display this this time in a DBU field strength display, because the DBUs are given in the recommendation. In this case, it's gonna be 32 DBU, and I'll show you how we can set that in the legend. And I'm gonna, since I'm in a different area now, I'm gonna go to this object, and I'll map that on the map so that I can go to it on the part of the globe where it's located. And as you can see here, my legend is already set to minimum of 32, and I can change it the same way that Daniel was showing you for the different SNR values. Since this is a DBU display, I can change my palette here. It's already at 32, so I'll leave it as that. But as you can see from this coverage, it looks like it's highly radiating everywhere. Because it is Omni, right? Now, I'll show you the effect of using an antenna, but before I do that, I want to show you how you can generate your own antenna patterns by going to the update gain calculator that we have here. Now, this is a very nice handy tool. It allows you to input some of the technical specifications that you might find for an ILS antenna. So to show you what I mean, I do have our training manual here, And I have a sample one that you can actually find in this link that is located here for an ILS antenna array. And this is a array consisting of 8 elements, as you can see here. It gives you different type of information, like for the 3 dB bin width. It gives you the front to back ratios, all that type of information that you need to input in the calculator is typically found in this sort of specifications tables. So once you do that, you can actually start to generate the patterns. So I'll just give you an example of some patterns that we can generate on the fly here. And I'm filling in the information directly from the table that I just showed you, but I'm changing it to comply with the objects that I have there on the network list. And that antenna had a unitary gain of 5 dBd. It gives you the option to update the gain on the network list for the object that you selected. And then, as you can see here, there's a reference to the ITU 2101, which is a recommendation that it allows you to generate antenna patterns for phased array antennas, even for 5G antennas and so forth. So it can be used for that purpose as well. In this case, I'm not using this mode, so it's gonna remain at no. But one of the cool features about that is that and which is the reason why we need to input the first adjacent frequency to calculate the horizontal or vertical spacings between the antenna elements. So a lot of users don't know that, but they do know, for example, the frequency plans. And in this case, for example, we have here an example of what is the channel separation for different type of aeronautical objects. So we have the ILS, as you can see, is 50 kilohertz here. So I'm inputting in megahertz, so it's gonna be a difference of 0.05 in this case. And if I wanted to, I can see just the preview, which is what I'm gonna do now. I can create a new antenna pattern, and by clicking on yes, it will update the antenna pattern automatically for the station that I selected. But I'm gonna leave it as no, because I only wanna look at the preview of what it looks like and the array antenna gain, which is important because that's gonna determine, depending on how many number of antennas or elements you have and the other features that we have here, it's gonna determine what your gain is, right? So you wanna make sure that you have the correct gain to calculate the correct energy that is coming out of the antenna. So in this case, it's the 23.06, which is what we already have input as the transmitter antenna gain for this object that already has the same antenna pattern. So as you remember, I showed that earlier, and we showed this pattern, but both of them get generated, and as you can see, this is what the H pattern looks like. Now, once I select the ILS object, and I'll go ahead and do the line of sight coverage, but for this station that has the antenna pattern already calculated, and I'm gonna hit run using the same parameters according to the ITU recommendation 1009 for ILS and VOR objects. I ran it, and then I'm gonna display it in dBUs again, and I'll overwrite the same coverage that I did before. And as you can see, it has a big difference or big effect on the actual energy and where it's being directed to. And where it's being directed to is very important, because let's say your airport is over here on the south and your energy is spewing out to the north, and there's something wrong, right? You got to orient your azimuth of the ILS to cover the area of interest. So to show you what the area of interest is, I'm gonna zoom in a little bit, and you can actually see the airport in there, but I'm gonna zoom in a little more so you can see it better. But you can see the airport there from the images. And you might be wondering, if you haven't seen this type of coverages before, why is your energy spewing out way beyond your little runway area? And that is because the area of interest is not necessarily just the airport. It does include the flight path area. And you know the flight path can be expanded to larger areas. You could come in from various different angles and land on the same runways here. Now, that is critical as well, because you don't want interference areas in none of those areas, as well as these areas here. So how do you know what the area of interest is in the critical areas? So for that, we can select the ILS, and we have the ability to generate what the ICAO calls as the designated operational coverage area contours. And once you click on it, you have a quick refresh. And if you go back to the map, now you've generated a DOC contour. And Daniel's gonna describe in the PowerPoints why this is important, and he's gonna show you a picture that has the different test points for interference. And later, I'm gonna show you the interference analysis on those test points, which are located in here. And those test points are basically just areas that you run some mathematical calculations and formulas to prevent interference given this coverage area. But right now, I'm just showing the coverage area, and this is what it looks like. And this is the coverage area within my critical area of interest. So this concludes this part of the presentation as well.
Okay, thank you, Joel. So I accidentally launched the poll, I think, in the middle of your presentation, but it was only for a few seconds. But I will relaunch. I'll try to relaunch the poll again at the end of the webinar, so everyone can continue to respond to it. So we're going to now go into the final part of the presentation, which will discuss frequency coordination and interference analysis. So I assume everyone can see my screen, and so we'll continue with this last part. So I'll give a little orientation into what Joel was just talking about in terms of the generation of the DOC, and where that methodology comes from for determining an area of interest for an operational coverage area. So the method that we're going to highlight today for modeling interference and performing frequency coordination between ground-based aviation, NAVAIDS, and other types of terrestrial communication systems is from a document known as the Handbook on Radio Frequency Spectrum Requirements for Civil Aviation. And it's published by the International Civil Aviation Organization, also known as the ICAO, which I mentioned previously. And this manual provides guidance to all civil aviation authorities on how to apply analytical methods and procedures for coordination of spectrum utilized by aviation NAVAIDS in pre-existing RF emissions. The ICAO handbook includes a detailed methodology for calculating all significant potential incompatibilities within an aeronautical volume of ground-based aviation NAVAIDS at a number of defined test points. This methodology is known as the General Assessment Method, also called the GAM. The GAM is based upon the need to protect stations in the aeronautical space. So we're going to have just a little bit more covered before we get to the end of the presentation, so bear with us just a little bit more. But again, the video will also be recorded, so you can watch it later. So the GAM is based upon the need to protect stations in the aeronautical radio navigation service at specified minimum separation distances from transmitting station antennas, depending on the aeronautical station, ILS or BOR, and the particular use made of that station. This is a broadcast or mobile station. Both the ITUR M1841 and the ITUR SM1009 incorporate the GAM into the recommendation. So the GAM produces what's called a DOC, is a designated operational coverage contour that Joel showed in his screen earlier. And this is this kind of a arrow kind of shaped contour that describes the approach toward the runway. So you have at the tip of the arrow the ILS localizer site, and you have along the line in the middle of the arrow the various test points that are kind of designated as potential interference calculation test points along the runway center line. So you have here on the table to the right the various test points, markings A, E, F, G, H, etc., and their distance from the ILS localizer site. And then the minimum height of the aircraft would be when performing the interference calculation at those test points. And then we have also points off the runway center line, and these are the points B, C at the edges of the arrow. And then we also have like XO and YO, X1, Y1, etc., all throughout the rest of the volume here, the contour. And those points are at different distances from the runway center line. And as you can see, they have different bearings relative to the runway center line in degrees. And it's assumed that the height for all those test points is at 600 meters. Is an example of the DOC contour generated in Spectrum-E, and the interference calculation that's produced will describe where there's potential interference at which test point, the margin of interference, and how the interference is calculated. So these are like out of band interference cases. There's combining different frequencies to calculate an intermodulation effect, essentially, and which test points where there is no interference found. So this is a coordination method that is employed for not just interference between NAVAIDS and broadcast systems, but also Vhf mobile transmitters, so LMR stations, etc. So Joe will go over that part, and that will conclude the presentation for today, and I'll try to regenerate the poll as well. Okay, whenever you're ready, Joe.
All right, so for the next demonstration, I have the ITU use case for how software should be in compliance with interference cases. They do sometimes the ITU for various recommendations provides these use cases, and in this case, there's one from the Geneva 84 documents that it's available, and it takes place in Canada. And I'm going to show you here, this is the 2 FM stations that are actually co-located and have an interference use case against some of those test points that Daniel was describing. So in this case, I'm going to show you the document as well in our training guide, and it shows the ITU use case, at least the screenshots from that case. And we have the FM transmitter site location, the DOC contour, and the hash line here is the area of potential interference. And as you can see here, the DOC contour is divided in the X's for the test points represented by the X's over here on the north and the Y's on the south. So that's the area of interest there. And we want to see if we can validate that. Do we get the same kind of results? So for that, we'll go ahead and go to the FM network. And we'll go down to the ILS VOR interference option and hit run on this. And as you can see here, we do have a lot of those X's, X1, 2, 3, 7, 8, 9, 7 again here, that are failing. This was shown in the PowerPoint as well. We have here the amount of interference at each point, and it does match the area of potential interference from the ITU use case that we use to compare and develop these interference mechanisms here in the tool. There is another one. As you can see, this is pretty friendly, user-friendly. It's very fast, and you get the results in tabular view pretty quickly. So that's something nice about the tool. I do have a different type of interference, is the aeronautical comm type interference. I want to show you that as well. So in here, because the previous interference case that I show you was based on the ITU 1841 and ITU 1009, along with the documents from the ACAO for interference purposes. There's a lot that goes in the background in the tool, for example, checking the type of object that you have. So I'm gonna go into that now. In the tool, we have the different type of objects that are supported. So in this case, we have the ILS, VOR, and COM object. And there's, if you select COM, for example, there's different type of objects that you can have on the airport that provide different types of services. Like the TWR is for tower services, approach service objects. You have objects that provide meteorological data. You have different type of objects that you could have layout everywhere along the runway or the airport
Hey,
close
John,
to
I
the
think
area.
you're. Oh, never mind. I'm sorry. Never mind.
Okay. Now I have a lot of these objects. As you can see, I have some VORs, some ILS, some COMs, and these are the tower service COMs that I have here. So I have set up a FM network here. So in this case, I'll select one to give an example. So when we run this function, it's gonna run the interference case, and it's gonna look at the COM interference as well, because I have COM objects. So when I do this, I'll hit run, and in a little bit, I'm gonna tell you a little bit of about what this is about after we see the result. So in the result here, we have, for example, interference for COM objects. So as you can see here on the bottom part, and it says that you have the interference at 1 kilometer at 2 meter height. You have the interference at 1.1 kilometer at 6 meter elevation height, and so forth, right? So, and for each type of interference, it gives you the interference power, but more importantly, it tells you some point like P1, P2, P3, where this frequency is getting interfering into those points. So that's something very important that I want to highlight, and I can only highlight it with some images. So in our training guide for COM interference, we see here that there's two special cases for COM interference. One is where the FM is located outside the area of interest, and the other one is where the FM object is actually located inside, right, that radius of interest. So depending on where your FM transmitters are, it will apply different formulas, and the points are gonna be different. So for example, in here, we have on the bottom, you can, I don't know if you can see that, I'll zoom in a little more, but you have this cylinder shaped object that is 3D going up in the air. And on the bottom, we have 0.1, then in the middle, 0.2, on the top, 0.3, which is the points that we're suffering interference in the result that we saw in Spectrum E. So there is a vertical 3D calculation that is being done. And if there is interference from an FM object outside that extends the radius of 1 kilometer, that's why you saw the 1 kilometer when I hit OK, then it will give you the interference in those different points, as you see here, point B, C, D, GHI, LMN, and so forth. So all of this is being ran under the hood, per se, when we run these calculations. And the calculations are pretty fast. They're displayed for you And I thought that it's very important for you guys to see the complexity of the 3D calculations that are being performed. It's not really a simple point-to-point calculation. It's very complex in terms of what it's doing and applying those formulas from the ICAO to get these results. So this concludes this part of the presentation.
Okay, thank you, Joel. So now we will go to the last part of the presentation, which are a regular question and answer. So I'm going to switch back to my screen. So there we go. So here's where we handle a few questions and answers. So we did receive a few questions. I'm going to relaunch the poll as well. Apologize for that, not for having done that a little premature earlier. So please, if you can, respond to the poll question. Again, the question is about how you are notified of this webinar. So you've got a few options. I did add an other if none of those options apply. So that would be helpful for our marketing purposes to better understand how you got notified of the webinar today. So some questions regarding the webinar today. So I'm going to go through a few of them here. I've answered a number of them through communications directly with the people asking the questions. One was regarding an update to the Icao Handbook. And yes, we will review that update. We know it's close to publication, and we will apply the relevant changes to our software if appropriate. So we understand that's in a draft stage right now. And I believe the ICAO updates that like almost on an annual basis, if I'm not mistaken, the handbook on frequency coordination. So it's one, will the video be made available on for viewing later? Yes. As with all our webinars, we do publish the recording on our YouTube channel. So the YouTube channel link is available in the handout. So feel free to download the handout, and I think it's one of the last pages as well. I think I can highlight it here. You have our contact details. If you have any other questions, you can email us at sales@spectrum.center. You can always go to our website, public.spectrum.center, to get more information. As mentioned before, you can go to spectrum.center and the request access link. Click on that link to request access if you wish to trial. Or the YouTube page is, Spectrum Center is kind of a common name, so it might be a little tricky for you to find it if you just search Spectrum Center. But there's a link there in the handout at the very bottom of the last slide. And click on that. That'll take you to our YouTube channel where you can see previous videos, and you will see this one there as well, which will be uploaded probably in about a day or so. Okay, so that pretty much concludes the questions. So the other ones that I've already answered directly to the people that were sending them. And yeah, please feel free to fill out the poll. I think we're just about complete. Actually, almost everyone's voted. So I'll be closing it in a little bit, another few more seconds. And if, again, you have any other questions, feel free to contact us. So, again, thank you, everyone, for your time. And we will schedule another webinar in March. Haven't confirmed the exact time, but probably within the next 2 to 3 weeks. And we'll notify everyone of the topic. We have several topics that we have in play. So we'll have to just make a decision on what that will be. And you'll get an update on all our normal channels of communication, email, the LinkedIn page, on our website. But we'll also see if other social media is relevant. We haven't seen a lot of success so far outside of LinkedIn for promoting the kind of communications that we typically promote. But if there's any suggestions, we're more than happy to hear about that. You can send us an email or a note. Thank you, everyone, for your time, and have a good afternoon or good evening. Goodbye.